Hi, this is Matt York, and I am covering exam 2 for Transport 2 in Dr. Carlos Coe's class. In this video, I will be going over part 2 since we just um, covered how to use dimensional analysis to form the dimensionless groups between the Reynolds number, Sherwood's number, Schmidt's number, and then we use Purcell's number to relate the Reynolds number to the Sherwood's number, I believe. So yeah, and going after that, now we are going to actually generate 100 pseudo experimental data points, and we're going to use a 10% normal distribution error to apply to the Sherwood equation, where it's a variable times the Reynolds number to another okay, I should say variable a to the Reynolds number or times the Reynolds number to the exponent of another variable b times the Schmidt's number to another variable c. And we are going to fit this data through linear regression and through minimizing the sum square deviation between the model and the data. And then finally, we will be plotting this data on a 3D and wireframe plots. So starting off first, we just want to define or call some toolboxes within Python that will help us solve this problem and do this linear regression and minimizing the square. So we're going to start out just by importing the most useful thing within Python, NumPy, which is numerical Python. So we're going to import NumPy as, I used to capital I think it's from import NumPy as NP. And then we are going to actually locate a toolbox within SciPy, which is within numerical NumPy, scientific Python tools. One of them is optimization. So we're going to do from SciPy to optimize. We are actually going to call we are going to import minimize to minimize the square later in this problem. And then we are actually going to locate another tool within Python, which is going to actually help us plot later in this problem. So we're going to go from plotly subplots. We're going to import make subplots. All right. And we need to do a couple more plotting tools we're going to be able to plot later. And so from, wait, are we importing? I forget. Plotly? No. Import graph objects as, I'm just going to G underscore O, because that way I'll know it's graph objects, not getting confused anywhere. And then from plotly.io as PyO. Okay, well, that's all we need to do at first. So I'm going to just go ahead and define, graphing objects. Okay, we're gonna keep that. Correct. Oh, is this np.graph objects? Sorry for my little error here. Usually this doesn't happen this early in this problem. NumPy as NP, SciPy optimize, plotly, that's what plot means. Let's try plot. Plot. All right, there we go. Wow, my mistake. That's not a numerical Python. That is a plot. In the plot toolbox of Python because we're plotting. So I should have called from there. Anyway, we have defined these, and these will all help us throughout. Well, we've actually not defined them, we've imported them from different toolboxes within Python to help us out within this problem. So now we're actually gonna go back to the problem. So we want to generate 100 pseudo experimental data points for our Reynolds number, our Schmidt's number, Sherwood's number. And when we relate them to the Sherwood's number, we need to have a 10% normally distributed experimental error. So first, we're going to just start by defining Reynolds number and Schmidt's number because we're not going to have to worry about the error until the Sherwood's. So we're just going to do Reynolds number. Oh, did I do something bad? There we go. Okay. Reynolds number is equal to, we're actually going to go to this random, what am I trying to say? A random distributor within numerical Python, and we're going to actually create a random uniform distribution because that's what it calls for in this problem with 100 experimental data points. So we're going to go to NP numerical Python, and we're going to go to a random distribution where it is also uniform because it's called for uniform distribution. And we are going to have this be from, it says a low and a high, so that's just our range. And here in this problem, it's 2000, so we're in 2000. And then to 3500 with our size, which we know we need 100 points. So we need 100 points uniformly distributed. And let's see if that gives us the array we're looking for. There we go. Perfect. So since Schmidt's number, we're doing something very similar. We're actually just going to go ahead and do, I'm just going to copy this, change this to Schmidt's number. And we're obviously going to have different range values. So we know that from the problem, it's 0.6 and 2.5. And we're also going to just have 100 data points there too. So doing this, let's check that really quick if it worked. You know what? I didn't see if that was the same one. So just to make sure. Boop. Let's see. Okay, yeah, that's better. Sweet. So we know that both of these are correct. And now we're going to actually just define Sherwood's number in regards to these other variables because we have this Sherwood's number equals 0.023 what times Reynolds number. I'm actually going to put this in parentheses. Reynolds number to the 0.83, and then that is multiplied by Schmidt's number. I'm going to actually put this in parentheses just to be careful again. And this is to the 0.44. So knowing this, this is now when we have to define our Schmidt's number, or not Schmidt's number, sorry, Sherwood's number. We have this defined as this equation, but we don't have it defined as a normally distributed 10% experimental error. So we need to define this as a 10% experimental error. So we're going to go to NP random again because we're randomly distributing these. But the thing is, instead, we're not doing instead of doing a uniform distribution this time, we're not doing uniform distribution. We're doing a normal distribution for this. That's normally or it's 10% normal experimental error. So it's normal distributing. Well, let's look at what we need to do within a normal distribution instead of a uniform distribution. It says we need to define a location and a scale size. So we know that our location of this error is Sherwood's. Oh, SH. Because this is where the 10% experimental error of the normal, 10% normal experimental 10% normal experimental error is going to occur is at Sherwood's number. So we're going to do it. Location is this variable we already defined as Sherwood's number. And the size is going to be wait, let's make sure it's size. It says scale because I don't know which one. Oh. Size, scale, float, or row float, distribution, spread, or width. Okay, so it looks like it's actually going to be scale. We're going to use not size. Because the size is like defining the array, which we don't want to do. We want it to be a scale of 10%. So we're going to do 0.1. What's it say? It says 10% normally distributed experimental error and fit the data. Okay. So I think it's actually going to be 0.1. So we're doing 10% of the Sherwood's number is going to be the error. So I think that's right. Let's see. See what we get when we do SH. Oh, wait, no, not there. We're going to delete this again so we don't get an incorrect error. SH, we get an array. So going past that, we are now going to, I'm now going to use linear regression to fit this data within this 10%. Yeah. So like, oh yeah, pretty much. Well, sorry. What the question is asking for us to do is fit this data to the form of the Sherwood's equation using linear regression method with Penrose's pseudo inverse, which is what I'm about to do. And then later in this problem, I'm going to do it by minimizing the square deviation between the model and the data. So right now we're going to go into the linear regression within Penrose pseudo inverse, which I'm actually going to start on paper before I do anything within the code, because when I do it within the code, it will get very confusing if I don't already show it within the paper. So I'm going to go ahead and define that for you right now, and then we're going to come right back to this code. All right, so now that we have inputted our equations into Python, well, I should say Google Colaboratory, we're now going to use this or figure out how we're going to solve this through linear regression. So the linear regression method with it's called the, let's see, the Penrose pseudo inverse method, we are going to show that on paper really quick before we code it because it's a little bit complex. So first of all, let's take the Sherwood's equation that we have here. So Sherwood's equals A times the Reynolds number to the exponent variable B. You can see that. All right, good. And multiplied by the Schmidt's number to an exponent C. So once we have this, but in order to simplify for it, we need to take these exponents down. So a method to use that is just, of course, natural log. So we'll take the natural log of the Sherwood's number equal to natural log of N. Oh wow, natural log of NA or of A. added to natural log of, oh wait, B times the natural log of the Reynolds number plus C times the natural log of Schmidt's number. So now that we have this, we're going to actually use matrices to do this linear regression. So first off, we know we have on this side a matrix C of ones corresponding to this ln of A. We have the ln of the Reynolds number. So the values correspond to the ln of the Reynolds number. And we have the ln of Schmidt's number. So these are going to be these values in this matrix C. We'll call this the design matrix C. And then we have an unknown matrix C. We're just going to call this B because it's the intercept, and I just like thinking of the intercept as B with y equals mx plus b being an intercept equation. So then we're going to set this equal to, of course, the matrix C of the ln of the Sherwood's number. So those values. So let's just simplify our, let's simplify what we're going to call these matrices. So this is a design matrix C, so I'm just going to call this matrix C D. And this is our intercept, so again, I'm just going to call that B. This is unknown. This is what we're looking for in the end. And we're going to set that equal to just L under Sherwood's. We can just keep that because that's pretty simple by itself. So now we're going to use a technique in matrices. It's actually called the transpose of a matrix C, which is when you flip the values of a matrix C upon its diagonal. And when you multiply that by the original matrix C, the transpose by the original matrix C, you actually get a square matrix C, which will help us, linearize these values. So what we're going to do is we're going to multiply both sides by the transpose of the design matrix C. And now that we've done that, to make this a square matrix C, we just need to figure out, okay, what are we actually trying to solve for? Well, like we just said, we're trying to solve for B, this unknown matrix C. We're trying to set equal to that. So what we're going to try to do is we're trying to get these two over here. Well, with matrices, you don't just divide it over like other math. This is just simple algebra. We're just going to do the inverse, of course. So we're actually going to do inverse of this transpose of the design matrix C times the design matrix C. And then by both sides, which means transpose of the design matrix C multiplied by the design matrix C. These would cancel out, multiplied by that intercept B, equal to the matrix C of the ln of the Sherwood's number, multiplied by transpose of the design matrix C, and that's multiplied by the inverse of the transpose design matrix C times design matrix C. Well, if we're just going to do this. So now that we have figured out these, these matrices in regards to the unknown matrix C, we'll set up an equation in regards to the unknown matrix C, B, the intercept matrix C. We're now going to use some of Python's features to create this within Python. So we had our design matrix C D, and we are going to use this function within NumPy called column stack, which we actually can, what am I doing? I gotta do a little rotation. Which we actually can stack arrays on top of each other. And since we created these arrays up here with our different numbers, we're actually going to utilize this column stack feature to stack these arrays into a matrix. So now that we have this, we're going to, now that we have called the column stack function, we're actually going to implement what we have in our column stack. So remember in our first one on our paper, we had in the design matrix, we had the ln of A, and it was just supposed to be ones that were representing the placeholder for the Shortwoods number. So what we're going to do is we're going to do np ones. It's a function within numpy, and it's like we can call ones that are like the actual Sherwood's number, which is so cool because it allows us to actually do that rather than just us kind of saying, okay, it's going to be ones like it. And then we're going to use our next one, np dot what is it, the log of the Reynolds number, I believe it was. Yeah, the Reynolds number. Let's go. Yeah, the Reynolds number, and then our last one, the Schmitz number. We have np log of the Schmitz number, I believe. Yeah, np dot log Schmitz. And that should give us this array. So let's just have that. Let's see. Let's call D. Wait, what? NP column stack. One's like SH. What did we do wrong here? NP is not defined. Oh, I think we have to get back and do that. Okay, so here, let's do this. Just need to these variables, sh, we can just delete that. And we can now call that. And let's see if we can call D. Yes, there we go. So we have our ones that are like the Sherwood's number using this numerical Python tool. And then we just do the log of the Reynolds number and the log of the Schmitz number because, because that is exactly what we did on paper. And that's what we want to do. We want to create this design matrix. Well, now we want to actually create our intercept matrix. Well, not create our intercept matrix. We already did create our intercept matrix. But we're trying to, we're going to input the equation we defined on paper with this intercept. So we created this equation relating the intercept matrix to the other matrices, and we're now going to just put that into code. So we're going to use NP, another function within numerical Python. This one's actually a linear algebra function because there's a lot of matrices within linear algebra. So we're going to call it from the linear algebra toolbox, if you will. And we're going to use we're going to use the linear algebra toolbox because that's what has matrices in it. And within this toolbox, there's a couple of things that we should probably note. One is it allows us to inverse the matrices, which we need to know or we need to have, as you saw on paper, we need to inverse matrices. It also allows us to use the transpose, which we are defined as flipping a matrix across this diagonal. And then we also need to use the, those are the only things we need to use within the linear algebra matrix. We just need to note that instead of multiplying using an asterisk in linear algebra, it actually uses an @ sign. That's just something that is noted within the linear algebra toolbox. Okay, so we just called the linear algebra toolbox, and we're going to do, based on our equation, we're going to show this again. I'm going to show you, so I'm not looking at other notes. We're going to show this again. So we have B equals the, it's up here. B equals the inverse of the design matrix C, or transponed of the design matrix C times the design matrix C. So we're going to do inverse of the design matrix C at sign times the transpose, which, let's see, is correct. And then we're going to do the transpose of the design. So multiplied by the design matrix C transpose, and multiplied by the log of the SH. Oh, I can't just do log. NP log. Oh my gosh, what am I doing? Log of. And this should give us our P. So let's see. Oh no, what did I do? NP. All right, so after a little bit of manipulation and figuring out my errors, I figured out that actually this D dot T was D, and this was D dot T, and it didn't work like that. So we're gonna go ahead and switch it back to what I found worked. So the design matrix transpose had to go first for some reason. I don't know if that's something within Python, but it works when I do it this way. So we're just gonna go ahead and do that. And we're gonna check what we have here and see if it actually took our design matrix, our transpose of our design matrix, matrix C, and our log of our SH, and got us the correct values. All right, so let's go back to the beginning really quick and see the values that we had for the Sherwood's number in these variables. So we had A was 0.23, while here it's negative 3.8256. So it's not correct. But if we look at B and C, we have 0.8365, 0.8635, sorry, and 0.83 for B. So those are very close, which is great. And we have 0.408 and 0.44. Awesome. So those two seem to be correct. So we're going to keep those two, B and C, and we are going to manipulate A. So let's see, how can we manipulate A, and what might be the problem with A if it's negative 3.8256? Well, we saw that we took the ln of A, and that's not what it's supposed to be. So we need to put A was just 0.23 down. It's not in an exponent. So what we need to do to remove that ln is we actually need to multiply it by E, put it to multiply by the exponential value. And guess what? Then hopefully it should give us the correct value. So we're going to E this, meaning, sorry, I kind of said that weirdly. So when you do an ln, the opposite of ln is putting E to the exponent of that value. And if we put E to the exponent of E to the negative 3.8256, I think that should give us the right answer. Go cancel out that ln. So let's go ahead and try that. So first we're going to, well, not first. Overall, we want to print the array that we're going to get back. So we're going to print an array. And within this array, we just want to print B. We have right there B0. Oh, wait, no, not 0. Sorry. 0 is the first term. That's the wrong one. B1 and B2. Because that would be the, come on. What's that there? That would be the second term because it starts on 0, the index does. So it'd be the second term, this, and the third term right here. But before that, we want to take the exponent when E it, and put it to the exponent of the E of this first term. So let's look within Python. We have, or numerical Python, of course, as we've done everything else in. We have this function just called exponential, and we can do that to that first term, which would be the 0th term in the array. If we do that, should get the correct answer. So let's see, we got NP exponent B. We want to print all of that, so it looks like it's good. And we get 0.218, 0.023, 0.0218, sorry, and 0.023, which are very close. Now, why are these values very similar to the three that we have in this equation, but not exact? Well, that can be attributed, oh my gosh, that can be attributed to our the fact that we have a 10% normal distribution error. And that gives us about a 10% normal distribution error. So we go ahead right there and say that we correctly have done the linear regression with Penrose pseudo inverse. So now we're going to go on to the second step of this problem, where we're going to do the, we're going to minimize the sum square deviation between the model and the data. So in order to do this, we need to first define a function so that we can have a sum square to minimize. So first, we're just going to call it sum square because, I mean, that's just easiest. That's what we're doing. We're summing the square. And we're just going to do that we're going to call it P because it's a parameter. And then we're going to go ahead and define what we want to return. So what we what we are doing by summing the square is we are setting the whole equation equal to 0. So we're going to take the Sherwood's number first. We're gonna use a predefined tool in Python. It's called the sum tool, and we're going to utilize this with making the square of making the equation equal to 0, therefore summing the square. So if we're going to do it equal to 0, we need to take our SH, our Sherwood's number, and we need to subtract the other side. So since we are parameter here, P is our array that we are having this array of sets of variables. Okay, here, let me re-say this because I feel like I'm confusing myself, so I'm definitely confusing you. So we have these three variables A, B, and C, and here we're using this new variable P as the parameter for A, B, and C. So we know that the first parameter, like the first term in the parameter is going to be A, second term is going to be B, third term is going to be C. So if we want to subtract the other side, then we're going to do the Sherwood's number subtracted by A, which would be the parameter at 0, because it's the first term, multiplied by the Reynolds number, which is to the second term in the parameter, B, or is to the exponent of the second term in the parameter, which is, so that is P of 1. And then this would be, I'm going to do these because this makes me feel better. I don't have to go back through it. I'm going to multiply that by the Schmidt's number, which is to the C, to the exponent of C, which would be the third term in this parameter. Therefore, the second term, because of Python, P of 2. There you go. And that's what it is. And then since we are defining a square, when you do a square, you actually you square both sides as well. You don't just set equals 0, you actually square both sides as well. So that's always a positive number. So we're going to actually take this whole equation of the square and we are going to square it. That's why it's called summing the square, because we're summing it and we're squaring it. And then after that, what is our goal here? We still need to minimize this sum square deviation. So we're going to use the minimize tool as we already called up here. We imported it from the SciPy optimize, and we're going to minimize the, well, let's see first of all what we have to do to use the minimize function within Python. So we're going to minimize a function. So what's our function here? It's sum square. And then we also need to have, oh, okay, these are our data points. Well, what are we given in this problem? We're given 3 data points for A, B, and C. So we can just go ahead and plug those in then. So let's go ahead and plug this array of data points we have. 0. What is it? 2 or 0, 2, 3. 0.83 and 0.4. And let's see what we get. Invalid syntax. Oh, I used a semicolon instead of a colon. Colon. Let's see. And that's beautiful. We get the 3 values of 0.2296439, 0.8229187, and 0.4399. Well, these are all very accurate. As we can see, these all give us the 3 values that we're trying to compare them to right here. So this is an easier way than the good old linear regression method. So if I had to choose one to use, I'd definitely use this one. But we are doing this 2 different ways, of course, to show that we could get this correct answers in each way. And so really quickly before I finish this part of the problem, I'm actually going to go back and set this equal to, I'm going to just call it answer. Because that way it's stored. Because if I just did it the other way, we only get it when we run this code. Well, this way, anywhere in our code, I can just put answer. Oh, forgot my, and we still have these 3 values stored into an array, which we want. So that way we can, if we plug in, let's see, we plug in, oh, I guess we printed it this way. I was going to say if we plug in B, but technically B wouldn't be, B only stores the correct values for the second and third. That's why we printed it up here. But that way we have the correct answers here. And if we want to go and have our correct answers here, we just type an answer. So yeah, thank you for paying attention to this part. I'm actually going to make another part because this video is already really long and I don't want it to take longer to upload, where I will plot the data and model a 3D point and wireframe plots. So that'll be all the plotting. I'm just going to work off of this code because I already have all my plotly subplots, make subplots, polygraph, graphing objects, and the poly.io. So I'm just going to actually come down here, but I'm going to go ahead and upload that into a 3rd video. So thank you so much for your time, and I really appreciate it, and I hope this helped. Have a great day.